Welcome to NPTEL. Myself Dr. Jayanto Das from Department of Metallurgical and Materials Engineering, IIT Kharagpur. I will be teaching you advanced materials and processes. This week we are discussing about nanomaterials, specifically focusing on the elementary consequences. And today we will continue the discussion on the effect of particle size and the elementary consequences on the modulation of different properties, because it has been said that once we reach to a very small particle size, we can get very novel properties, and those are unique and not possible to get such properties in the bulk scale material. Now, you may recall that we were talking about the modulation of the properties due to the elementary consequence or the size effect, and in the last class we have discussed about the effect of surface, very specific on the surface area and so on, and also the structural magic number. And today we will be focusing on the thermal phenomena, the diffusion in a very small particle, or let us say the vibration effect, and now related to surface there is a curvature effect, the strain confinement within a very small particle, how does it occur and what is the meaning of it, and the quantum effect, means we will be talking about the electron density inside a smaller size particle. So, those issues can give a material or new properties will evolve in such kind of nanomaterial. There is no doubt that when we decrease the particle size, we have large number of atoms present at the boundary region or at the surface. Okay. So, this is a bulk solid. However, if we consider a single particle, then majority of the atoms are present on the surface only. So, here these are the surface atoms. So, let us continue this idea and let us have a look at what is the effect of a surface curvature. Here the radius of curvature of a very small particle will decrease, means if I have a 10 micrometer size particle and 10 nanometer size particle. So, the radius of curvature is smaller in case of 10 nanometer, there is no doubt about it. Now, the vapor pressure, which said that the vapor pressure which is in equilibrium at the surface, which is proportional with basically exponential 1 by d. It basically said if the particle size is very small, the vapor pressure is very high, okay? And atoms always try to jump into the vapor state for a very small particle. And let us have a look at when I have a infinite size particle and a smaller particle. I am taking here the ratio of the vapor pressure. In that case, the particle diameter as it comes down, let us say 10 nanometer, then automatically the vapor pressure goes even reaches up to almost like 90%. So, this is a phenomena is very much important of during sintering operation. How does it occur and what is the other consequence of it? Let us have a look at here. This is a particle that is basically alumina particle. Alumina means Al2O3 particle, and here is also another Al2O3 particle, and this particle size is very small. You can see almost having a diameter of 40 to 50 nanometer only, and here the atoms will tend to vaporize and they will come and join here, and these two particles will join together. That is the idea. Okay. And it is much more easier when the particle size is small, because the vapor pressure is very high at the surface. So, the mechanism of such atomic transport and phenomena is explained in this diagram. You see here there are two particle, and these two particle has two different curvature. So, here the curvature is basically the positive, and this is the region where the curvature is negative. This is the negative curvature and this is the negative curvature. Okay. So, in that region of negative curvature, the atoms will always try to join. Yes, atoms will always try to join. From where? From here it will come and it will join here. The question here, that how does it really occur? So, if we think about a surface, actually if the atoms are present, the nearby surrounding atoms has some bonds, you agree with that. However, if in case of such a scenario, when I have material and atoms will come and join, then they can make more number of bonds. So, atoms will come and join. So, they have more number of bonds in this case, for a less number of bonds. So, this one is more energetically favorable process. So, from a less number of bonds atom have, they will always tend to go where they have more number of bonds from a less number of bonds. So, atoms will come from here and will always try to join here. So, this is the process, the effect of the negative curvature. So, here this is the negative curvature and here this is the positive curvature. So, negative and positive curvature. So, this is a typical material transport phenomena that is governed by the curvature effect, and this curvature effect become more and more stronger when the particle size reaches to a nanometer scale. Now, there are very important such curvature effect, and just a few seconds ago we told about the pressure and the diameter of the particle, they are inversely proportional. So, this is a typical Gauss Laplace formula. The pressure difference between the interior and the, he was talking about the liquid droplet actually. So, the pressure in the interior and at the outside of a droplet, the difference of their pressure is proportional with the inversely proportional with the diameter of the droplet. So, that was basically the idea. And now, if we think about the compressibility of a nanoparticle, then this compressibility is 1 by V 0 and basically del V by del P, means how much is the effect of pressure on the change of the volume. And as we know that if I have a cube or like that, any of these dimension that has a cube relationship with the volume, okay, whether it is 4/3 pi r cube or some any other dimension, means sphere, cube or whatever, it does not matter. And in such a case, you will agree by joining these two equation, then I will get basically gamma by d, which is linked with, let us say, the compressibility and del A by A. Here del A is basically the lattice parameter. Okay. So, if I think about it is as a unit cell, then it is basically a cube. A is the lattice parameter, let us assume. So, the lattice parameter will change with the diameter of the particle. This is the equation that we basically get out of this. So, since the surface energy increases as the particle size decreases, because the radius of the curvature is basically the decreases. So, the lattice parameter is also reduces when there is a decrease of the particle size, and this is a very important phenomena that one can look at. So, let us say I have a aluminum specimen and I am keep on decreasing its particle size, and here let us say this is a bulk material lattice parameter of aluminum, and if we measure then from let us say 26 nanometer to 8 nanometer, the lattice parameter will decrease. So, means the atoms are more compressed, okay, in a nanometer scale. So, this is of the very unique observation and consequence of the surface curvature. Now, the other part is the strain confinement. This is occur because of the very small particle size. What do we mean by strain confinement? Let us forget about at this moment a nanomaterial, but consider that I have a infinite size crystal and I am putting a dislocation in it. In that case, I have such a situation where I have some extra half plane here. So, mu is the shear modulus and B is the Burgers vector, R is the radius of the dislocation stress field. So, dislocation stress field will be surrounding that edge dislocation and C is a cutoff parameter. Then we can simply estimate that the strain energy of a perfect edge dislocation loop, which is Ws, which is equivalent to mu into B square by 4 pi into logarithmic of R by C. However, here is a very basic assumption that there is no other stress field acting on this dislocation, means there is maybe a grain boundary, this may be a grain boundary or maybe other dislocation and maybe other stress field that is not influencing on that edge dislocation. So, if crystal size is infinite, then there is no grain boundary effect or no other effect, and this is the equation that we can derive. Okay. And this is already available in many of the mechanical metallurgy textbook that you can follow. However, the strain energy of same dislocation, if I am putting inside the nanoparticle, means my particle size itself is like this and I have a dislocation inside it. Means I have a extra half plane inside that particle. What is the resulting effect? So, here the same constants and others are there, but I have introduced two term, one is capital R minus R d. So, R d is basically the distance between the dislocation line and the surface. So, nanoparticle size is R. So, here is the size, that is R, and the distance here, that is actually the R d, small d. So, in that case you can see that the smaller the particle size, the stress field of the dislocation is basically the reduce. What does it mean? It basically means that here this value is always less, na? The value is always less, yes. So, it will impose a force on the dislocation and it will try to eject out the dislocation on the surface. So, what will happen? If the particle size becomes small, this dislocation will come at the surface, means the extra half plane will go away. So, it will always try to be a perfect crystal. So, a nanoparticle below a critical size have a, this is why we call it as a self healing characteristic. So, no defect and dislocation, okay, they are can be present and they all are unstable and therefore, they will be ejected out at the surface, and this is as a strain confinement due to the smaller particle size. So, this is a very interesting observation when the particle size reaches to a small size. And now, there is another phenomena that is associated with the smaller particle size, that is the thermal phenomena. Now, for any of the substance, they have some thermal energy and that energy is linked with K and T. Here K is the Boltzmann constant and T is the temperature. So, you can think about that I have a isolated nanoparticle and the energy is basically K and T. Okay. So, if we are talking about that the total energy, that is U, which is a function of the volume V, V is here is the volume. So, it will be equals to k T, but suddenly due to the reduction of this volume, then the same energy will not be there, because I have divided the particle into 4 pieces, let us say. So, I have suddenly decreases the volume of the particle. Okay. So, I have now 1/4 of the volume. So, there is a imbalance of that total energy, that is k T, or the net energy of a small particle which is coming out of a very big particle is less than k T. So, there will be a thermal instability. And what will happen if that thermal stability instability occur? So, the nanoparticle basically will tend to lift to a or make a jump, okay, with a certain distance. And how it is associated with it? Because U V or U, that is the energy associated with the volume, that is linked with the rho, that is the density, the volume, and the x is the jump, that will be equals to the k T. And we can simply for the sake of mathematics, we can calculate it. Let us say I have taken a zirconia particle which has a density of 5.6 into 10 to the power 3 kg per meter cube, and let us say at room temperature the thermal energy would be lift to a particle, let us say something like 1100 nanometer, which is almost the same scale of the size of the particle. So, this particle will try to lift, and this is a very similar observation people have seen, that the nanoparticle always tend not to be very much stable at a localized place. We can also give some sort of light or some other energy it can absorb, and it will tend to do the same thing. So, from a particular state, if it gets some activation energy, then it will always go to a other state. So, this is just a energy barrier if from a due to the jump from one state to other state of a nanoparticle. So, we are talking about, let us say, absorbing from the surrounding, the absorbing of energy, that is a thermal phenomena, and then the particle will try to jump and go to a second state. So, these are one of the very important size effect in a nanoparticle. Now, if we consider let us say a simple cantilever, means I have a body, rigid body, which is attached to a wall, and I am leaving it, and they have their own vibrational frequency, that is nu, let us say, in a vibration mode, and the rod has a length of L, okay, and the diameter is basically d, which is fixed at a end. So, we can estimate this with that how much will be the vibration of that particular beam. So, that basically scales with L square E by rho, and if we consider d and L and so on, then ultimately for a size it will come that nu 1 is proportional to 1 by L. Okay. So, you can see the longer the length of the rod, the frequency will be less, whereas the smaller the size, the frequency will be very high. Okay. If this basically decreases to a nanometer scale, the equation itself says that. Okay. And now, I can estimate, or one can estimate the basic frequencies for a bending vibration of a cylindrical rod with a aspect ratio of 10 of different lengths, let us say for iron, or let us say for a carbon nanotube, okay, which is also very famous advanced material. So, if the length of a rod is 0.1 meter, or let us say I have 10 to the power minus 8 meter. Okay. So, this means basically let us say something like 10 nanometer size. The frequency of iron in hertz will be 520 to 10 to the power 9, This is basically scaling with the simple length. So, the smaller the size, it just inversely proportional. So, the vibrational frequencies of nanomaterial is almost 10 to the power 9 times higher than any of the larger meter size length scale, and that is very much clear. Now, if we consider for a carbon nanotube and if we put the density values, then for 10 nanometer size carbon nanotube, the vibrational frequencies is 10 to the power 10 in case of hertz. So, this is a very high and enormous change of the vibrational frequencies when we reach to a very small size. So, this is also another size effect on nanomaterial. And now, since we have talking about joining of two particles, there is a need of the atomic transport and also there is a need of diffusion. So, how size effect affect on the diffusion, that we should try to think about. So, diffusion in any material is explained by the law of Fick's. So, Fick's has two laws, and one of those laws says actually that the x squared, that is the diffusion mean square diffusion path, which scales with d into t. Here d stands for the diffusivity and t is the time. Okay. And it has been observed that this time scales with the square of the particle size. Okay. Means the smaller the particle size, the smaller the time required for diffusion. That basically said that. Now, you can think about that I have one gold nanoparticle, I have copper nanoparticle, yes, and they all have, let us say 2 nanometer size, 2 nanometer size. So, they will if you think and compare with a micrometer size particle, then the homogenization time means gold atom will go into copper and copper will go into gold. This solubility we are talking about, it will be a instantaneous. So, alloying will cause instantaneous, because alloying need diffusion, and I am talking about in the solid state diffusion actually. So, in a solid state itself, the two particles will join together very fast. So, the homogenization time, if we calculate, let us say for a particle size of 10 micrometer and 5 nanometer, let us assume that, and let us assume that in one case I have 300 kilojoule per mole activation energy, another case I have 200, and from that equation at a temperature let us say 1000. So, this is almost 10 to the power 7 times smaller time scale that one need. So, let us say a general time, that is 1000 second for homogenization, that will reduce by 10 to the power 7 times, or let us say at 700 K, or let us say at 400 K. So, you can see at 400 K the 10 to the power 26 will come down to 10 to the power 19. Okay. So, it is almost 7 times. So, at any given temperature scale, the homogenization of two different nanoparticle is much faster than any other micron or larger size particle. And as an engineer, we can use this. How to use it? Let us say we can use as a gas sensor, the gas atom will diffuse into a sensor body. So, the atoms will diffuse into the sensor body, and if I make this as a very small, then the signal will be much more faster. Means here I have a sensor and here is the gas atom. Let us think about, let us say oxygen ion, or let us say some carbon monoxide gas and so on. Okay. And here there is couple of devices that has been produced recently by Professor Hahn at TU Darmstadt, Germany. So, tin oxide is one of such kind of material that is used for gas sensing. Okay. So, I have those electrode, and then the nanoparticle of tin oxide are deposited, and they have the contact lead which will give you the signal on a alumina substrate. So, let us say here I have oxygen or all let us say carbon monoxide, they will come and on the tin sensing particle, and then there are electrical contacts and the substrate is the electrical contact and it will give the signal. So, the faster or the response will be very high when we are thinking about a sensing application of nanomaterial. So, you can see just by using some fundamental principles, we can find out a large potential application of this nanomaterial. Or let us say if such a case, if the grain diameter we are thinking about, let us say here this is a nanometer grain diameter and the sensitivity of your device means I am talking about basically sensing device. So, here it basically increases let us say 14 or 10 times higher when we reaches to a tin oxide particle size of 5 to 10 nanometer. So, this is also a vast and wide application areas of the nanomaterial. And then one of the very fundamental or elementary consequence is the quantum effect. So, first we need to talk about what we really mean by this quantum effect. Usually in our typical textbook in school, we have learned that the energy is distributed in different states. Okay. So, let us say in case of a conductor means let us say I am talking about a metal, let us think about a metal. So, we have conduction band, we have valence band and we have some occupied state. So, electrons are present in this valence band and they can easily go to the conduction band and there will be easy flow of the electrons, and that is why most of the metals or all the metals are basically the conductors, because there is no energy gap between the valence band and the conduction band. Now, let us come for discuss about a insulator. In insulator there is a large gap of the energy and this gap is very high, and therefore, electrons are always in the valence band and does not go into the conduction band, and that is why they are insulator. However, in case of semiconductor, this gap is relatively narrow, and if there is a energy is given to the electron to go to the conduction band, then we can get some conductivity, right. And this is basically the fundamental principle, means here we are all talking about the electron density distribution at the different state. Now, let us think about what does really happen in case of nanomaterial. In case of nanomaterial, we have talked about 3D nanomaterial or let us say 2D or let us say 1D or 0 dimension and so on. So, in case of 3D, I am showing you a plot with the energy versus the density of the states. So, here you will see that the electron, all different energy, the electrons are distributed. Okay. So, there is almost no problem at all. However, if I think about a 2D nanomaterial, okay, a 2D nanomaterial means basically that such kind of flat. So, here the electrons are somehow distributed for a particular level of or a range of energy for certain numbers. Okay. Now, the extreme point here is in case of 0D, when I have a small 0 dimension particle and the energy is always is fixed for a particle energy level, and this is the number of those density of states, and this is known as a quantum dot. So, the energy is or the electron is present in a particular well. So, due to the effect of a very small size, such kind of confinement of the quantum or the electron will occur. So, the electrons are always confined with a particular energy level. So, this is what I want to mean. In case of 3D, the electrons are fully delocalized. Okay. So, you can see the distribution of different energy level of the electrons, they are fully delocalized. Whereas, in case of 1D and 2D, in this case or that case, so let us say the energies are basically here, this is a confined and here it is the delocalization of the electron density states. And this density of the states are very much important parameter to tune the properties, and you can believe that there are so many number of properties that occur due to such kind of in case of quantum dot, and quantum dot is one of the very wide application areas in case of materials. So, like here the photo emission spectroscopy, here also the quantum confinement is very much important, specific heat, thermo power effect, or let us say the excitation in a semiconductor, or let us say the superconducting energy gap, here is also important. And then let us say the single photon source and biological tagging, optical memories, and the most important are the photonic structures. So, if we can produce such kind of very small particle size, the quantum confinement will occur. So, here the electrons are confined on a very discrete energy level. Okay. So, these are the numbers and here is the energy, and this is one of the very important promising elementary consequence that is very much important in case of nanomaterial. So far in this discussion, through this discussion we completed these elementary consequences in a smaller particle size and what is its effect on the different properties. With this we finish our discussion today. Thank you very much.